I want you to do something very simple. I want you to look at a lamp in the room or a light bulb, and I want you to reach over to the switch and flip it on. Click, and there it is. The room is full of light. Instant. Immediate. It feels simultaneous. Your finger moves. The light appears. There is no gap. There is no waiting. It feels like light is everywhere all at once. For thousands of years, human beings, very smart human beings, much smarter than you and me, they thought that light was instantaneous. They thought the speed of light was infinite. And why wouldn't they? If I throw a rock at you, you see me throw it, you see it coming, and then bonk, it hits you. You can watch it travel. But light, you open your eyes, and the distant mountains are just there. You don't see the image of the mountain traveling toward you. It just seems to exist. But nature is tricky. Nature holds her secrets tight. And usually when our common sense tells us something is obvious, nature is waiting around the corners to hit us with a pie in the face. Because light does travel. It moves. It is a thing. It is a traveler. And the story of how we found that out and why it moves at the speed it does is perhaps the greatest detective story in the history of science. So let's go back. Let's go back to Galileo. Now, Galileo was a man who didn't take anybody's word for anything. If Aristotle said heavy things fall faster, Galileo said, let's throw them off a tower and see. So Galileo, he suspected that light had a speed. But how do you catch something that fast? He came up with an experiment, a very simple, very human experiment. He got two guys with lanterns. He put one guy on a hill, he put the other guy on another hill, maybe a mile away. The plan was this. Guy number one uncovers his lantern. Flash. As soon as guy number two sees the light, he uncovers his lantern. Flashback. Galileo stood there with a timer, well, a pulse beat or a water clock, and he tried to measure the delay. He tried to measure how long it took for the light to go there and come back. And what did he find? Nothing. He found that the light was too fast for his reflexes. The delay was zero, or at least the delay was so small that it was masked by the time it took for the guys to just move their hand. So Galileo failed, but he was smart in his failure. He didn't say light is infinite. He said, if it has a speed, it is extraordinarily fast, faster than I can measure on a hilltop. He realized that a mile is nothing to light. A mile is a joke. To catch light, you don't need a bigger hill. You need a bigger laboratory. You need space. And this is where the story gets wonderful. We move to the year 1676. A Danish astronomer named Ole Rømer. Rømer wasn't looking for the speed of light. That's how science works, usually. You are looking for the bathroom and you find a gold mine. Rømer was looking at Jupiter, specifically the moons of Jupiter. Io, the little moon Io. Now, the solar system is a great big clock. It is the most precise clock we have. Now, Io goes around Jupiter, round and round, and every time it goes behind Jupiter, it gets eclipsed. It disappears, and then it comes out the other side. It's regular. Tick-tock, tick-tock, tock. It happens every 42 and a half hours. So Rømer is watching this, and he's writing down the schedule. He's making a timetable. Okay, the next eclipse should happen next Tuesday at 9 p.m. But then something strange happened. When the Earth was close to Jupiter on the same side of the sun, the eclipses happened right on schedule. But 6 months later, when the Earth swung around to the other side of the solar system, moving away from Jupiter, the eclipses started to be late. And they were lagging behind, minutes late. And then as the Earth came back around closer to Jupiter again, the eclipses caught up. They got back on schedule. Now, most people would have said, oh, my clock is broken, or Jupiter is wobbling. But Rømer, he had an imagination. He had a physical intuition. He said, wait a minute. The moon isn't late. The news is late. Think about that. The news is late. He realized that the light, carrying the image of the moon, the picture of Io coming out from behind Jupiter, it had to cross the gap between Jupiter and Earth. And when Earth is on the far side of the solar system, that gap is bigger. It's an extra 186 million miles or so. The light had to travel that extra distance. And that took time. It took about 16 minutes to cross the width of Earth's orbit. Romer did the math. He divided the distance by the time. And for the first time in human history, we had a number. We knew that light was not magic. It was a messenger. And the messenger had a speed limit. It was fast. Oh, it was terribly fast. But it was finite. And that changes everything. Because if light yet takes time to travel, it means when you look at Jupiter, you're not seeing Jupiter now. You're seeing Jupiter as it was 40 minutes ago. When you look at the sun, you're seeing it 8 minutes ago. If the sun blew up right now, we wouldn't know it for 8 minutes. We'd be sitting here on the beach, happy as clams, while the sun was already dead. You look at the stars, you were looking at ancient history. We are trapped in a bubble of the past. We can never see the now of the universe. We can only see the then. So we found out it moves. But that brings up the next question, the big question. The question that leads to the title of this talk. What is it? What is moving? Is it a stream of particles, like little bullets? Newton thought so. He called them corpuscles. Or is it a wave, like sound, like ripples in a pond? This was the great war of physics for 200 years. The particle guys versus the wave guys didn't. And in the 1800s, it looked like the wave guys had won. We did experiments, the double slit experiment that showed light interfering with itself, wiggling, canceling out. Only waves do that. Bullets don't cancel each other out, they just pile up. So, okay. It's a wave, but a wave of what? If I shout at you, that's a sound wave. What is waving? The air. The molecules of nitrogen and oxygen are compressing and expanding, shoving each other. If I make a wave in the ocean, the water is waving. You see, common sense says, to have a wave, you need a medium. You need stuff to wiggle. You can't have a wave in nothing. That doesn't make sense. A wave is a property of a substance. So the physicists of the 19th century said, okay, light is a wave. It travels through the vacuum of space. But space can't be empty. It must be filled with a fluid. A mere subtle, invisible jelly that fills the entire universe. And they called it the luminiferous ether. The ether. It sounds like something from a fantasy novel. They said this ether was everywhere. It was inside your head. It was between the stars. It was stiffer than steel because light travels so fast. The medium must be very stiff to vibrate that quickly. But it was thinner than air because the planets moved through it without slowing down. It was a magical substance invented to explain the wave. And everybody believed in it. It had to be there. But then came a man named James Clerk Maxwell. Now, Maxwell wasn't looking at light. Not at first. He was looking at electricity and magnetism. Before Maxwell, we knew about electricity, sparks, batteries, lightning, and we knew about magnets, compasses, but they seemed like two different things. But experiments started to show that you were connected. If you move a magnet near a wire, you create electricity. If you run electricity through a wire, you create a magnet. They were like two sides of the same coin. They were dancing with each other. Maxwell, he sat down and he wrote equations. He tried to describe this dance mathematically. He found that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So imagine this. Imagine you wiggle an electron. Just shake it. That creates a changing electric field. That changing electric field immediately creates a magnetic field next to it. But that magnetic field is changing too. So it creates an electric field next to it, which creates a magnetic field, and so on, and so on. The fields pick themselves up by their own bootstraps, and they fly away from the electron. They travel through space, self-propagating. Electricity creating magnetism, magnetism creating electricity, a chain reaction, a wave. Maxwell looked at his equations and he asked, How fast does this wave go? He calculated it based on the strength of magnets and batteries, just pure numbers from the lab, and out of the paper popped a number, 300,000 kilometers per second. Maxwell must have fallen off his chair, because that number was exactly the number Roma and the others had measured for the speed of light. It wasn't a coincidence. Maxwell realized the great truth. Light is an electromagnetic wave. The light you see, the colors of the rainbow, the warmth of the sun, it is just electricity and magnetism vibrating in empty space. And this is where the mystery gets deep, because Maxwell's equation gave us speed, E, the constant. But speeds usually depend on who is looking. If I am on a train going 60 miles an hour and I throw a ball forward at 10 miles an hour, to me the ball is going 10. But to you, standing on the ground, the ball is going 70. 60 plus 10. Velocities add up. That's how the world works. So, physicists thought, okay, light travels at sea through the ether. So if I am in a rocket ship moving through the ether and I shine a flashlight forward, the light should go faster. Or if I move away from the light, it should catch me slower. They built a machine to measure this with the Michelson-Morley experiment, the most famous failed experiment in history. They measured the speed of light in the direction the Earth was moving, and they measured it sideways. They expected a difference. They expected to see the wind of the ether blowing past the Earth, and they found nothing. Zero. No matter which way they pointed the machine, no matter how fast the Earth was moving, the speed of light was exactly the same. It didn't make sense. Imagine you are running down the street at 15 miles an hour, and a car passes you at 30 miles an hour. To you, the car is only going 15 miles an hour faster than you. But nature was saying, no. If you run next to a beam of light, it still passes you at the speed of light. You can chase it in a rocket going 99% the speed of light, and the beam still flies away from you at exactly c. It's as if you were standing still. How can that be? How can a speed be the same for everyone, no matter how fast they are moving? The math was broken. The intuition was broken. The universe was playing a joke on us. And for 20 years, the physicists sweated. They twisted themselves into knots trying to explain it. They said, maybe the rulers shrink when you move. Maybe the clocks slow down. They were getting close. But they were afraid to take the final step. They were afraid to throw away the ether. And then a clerk from the patent office in Bern, Switzerland, picked up his pen. A young man, Albert Einstein. He looked at the problem and he said, what if the experiment isn't wrong? What if our idea of time is wrong? This is the hinge of history. Einstein said, let's assume Maxwell is right. Let's assume the speed of light is constant. It is the law of the universe that T is fixed. If speed is distance divided by time, and if the speed can't change, then the distance and the time must change. Boom. Relativity. To keep the speed of light constant, space itself must squish, and time itself must stretch. If you move fast, your clock ticks slower. Your ruler gets shorter. Not as an illusion, as a physical reality. Why is light so fast? Or rather, why is light the limit? Because light is the speed at which the universe communicates. And to understand why it's a limit, we have to talk about what speed really means. We have to talk about causality. Because it turns out the speed of light isn't really about light at all. Light is just the thing that happens to go as fast as possible. The speed limit, c, is the speed of cause and effect. But I'm getting ahead of myself. Let's stop and think about the why. Why 300,000 kilometers per second? Why not instant? Why not a million? Imagine if the speed of light was infinite. If light was instant, then every event in the universe would happen simultaneously to every observer. You would look at the sky, and you wouldn't see the past. You would see the present. But more than that, if signals could travel instantly, gravity would travel instantly. If the sun disappeared, the Earth would fly out of orbit instantly. It seems nice, tidy, but Einstein showed us that if you can send signals instantly, you can send signals into the past. You break the timeline. If you can go faster than light, There are reference frames, ways of looking at the universe where the effect happens before the cause. You die before you're shot. The glass breaks before you drop it. You answer the phone before it rings. The universe, above all else, seems to want to protect the narrative. It wants to make sure that A happens, then B happens. So there must be a limit. There must be a maximum speed that information can ripple through the fabric of reality. We call it C, and light, because it has no mass, because it carries no baggage, it goes at the limit. It puts the pedal to the metal and goes exactly as fast as the universe allows any information to move. It isn't that light is special, it's that light is lightweight. Literally, it has zero mass. So the question, why is light so fast, is actually the question, why is the universe built with a speed limit? And to answer that, we have to look at what happens when you try to fight it. What happens if you try to push an electron to the speed of light? We do this. We do this every day in accelerators, like the Large Hadron Collider. We take protons and we kick them. We pump energy into them. They go faster. 90% the speed of light. We kick them again. 99%. Kick them again. 99.9%. Kick them again. 99.999999%. We pump enough energy into them to light up a city. And do they reach the speed of light? No. They get closer. But they never touch it. Why? Because of E equals mc squared. Energy and mass are the same thing. When you give energy to an object to make it move, you're actually making it heavier. Well, not heavier in the sense of putting it on a scale, but it gains inertia. It becomes harder to push. The faster it goes, the heavier it gets. So you need more energy to push it faster. But that energy makes it even heavier. It's a vicious cycle. As you approach the speed of light, the mass of the object approaches infinity. To reach the speed of light, you would need infinite energy. And there isn't infinite energy in the universe. So matter, you and me, the spaceships, the protons, we are trapped. We are condemned to live below the speed limit. We can never reach the horizon. But light, photons, they cheat. They have no mass. They start with zero, so they don't have to accelerate. A photon doesn't start at zero and speed up to C. The moment a photon is born, when an atom jiggles and spits it out, it is already going the speed of light, instantaneously. It cannot go slower. If it exists, it moves at C. If you slow it down, it dies. It gets absorbed. So light lives on the edge. It lives on the boundary of reality. And living on that boundary, things get very, very strange for the photon itself. Have you ever wondered, what does the universe look like to a beam of light? If you could ride a photon, what would you experience? This is a thought experiment Einstein had when he was 16 years old. He imagined chasing a light beam. Let's apply what we know about time dilation. We said, the faster you move, the slower time ticks for you. If you go 99% the speed of light, a year for you is 7 years for the Earth. If you go 99.999%, a year for you is 1,000 years for the Earth. Now take it to the limit. If you hit 100%, if you hit C, time stops. Zero. For a photon, time does not pass. It leaves the surface of a star in the Andromeda galaxy. It travels for 2 million years through the void. It hits your eye on a Tuesday night. To us, that trip took 2 million years. To the photon, it was instant. The moment it was born, it hit your eye. The birth and the death were the same moment. For light, there is no distance. There is no time. The universe is a single point of contact. This is a profound thing to think about. We think of the universe as this vast, lonely place full of empty space. But for the light that connects us, the space doesn't exist. Light stitches the universe together. It brings the news of the stars to us instantly from its perspective. So why is light so fast? Because it is the messenger that transcends time. Because it has stripped away all the weight of matter so that it can show us the structure of space-time itself. So we have this speed limit, 186,000 miles per second, 300,000 kilometers per second. It's a big number to us. But on the scale of the universe, it's actually kind of slow. Think about it. It takes light 100,000 years just to cross our own galaxy, the Milky Way, just one island of stars. If you tried to call someone on the other side of the galaxy, you'd say hello. And 100,000 years later, they'd hear it. Then they'd say hi, and another 100,000 years later, you'd hear it. It's a terrible way to have a conversation. So why is the limit so slow? Why does the universe have such a lack? Well, let's look at what c really is. We call it the speed of light, but that is bad branding. It's false advertising. Light is just the most famous thing that travels at that speed. But gravity travels at that speed too. If the sun vanished, Earth would orbit the empty spot for 8 minutes before flying off. Gluons, the particles that hold the nucleus of the atom together, they travel at that speed. Anything that has no mass travels at c. So c isn't a property of light. It is a property of the fabric of space-time. It is the conversion factor. You know how you can measure distance in inches or in centimeters? And there is a number 2.54 that converts them. Well, Einstein showed us that space and time are the same thing. They are just different directions in the same map. But we measure space in meters, and we measure time in seconds. We use different units because we are biological creatures who perceive them differently. The speed of light, c, is just the exchange rate. It tells you how many meters of space are equal to 1 second of time. And the answer is 300 million meters equals 1 second. That is the ratio of reality. So asking why is light that fast is like asking why are there 100 pennies in a dollar? Because that's the exchange rate. Now, I want to talk about something that really bothers people. They say, okay, I get it. Light is fast, but why can't I go faster? Why can't I build a rocket that pushes harder? If I'm going 99% the speed of light and I fire a thruster, I must go faster. And the answer is, you do, but you don't go faster through space. You go faster through time. Wait. Let me back up. This is the most beautiful idea in relativity. It's called the four-velocity. Imagine you are in a car. You can drive north or you can drive east. If you are driving purely north at 60 mph, you are making zero progress east. If you turn the wheel and drive northeast, you are now moving a little bit east, but you've slowed down your progress north. You've traded some north speed for east speed. Now Einstein says everything in the universe, you, me, this cup of coffee, we are all moving at the speed of light all the time. But we are moving at the speed of light through space-time, the four-dimensional map. Right now, you are sitting in a chair. You are not moving through space. Your speed in space is zero. So all of your speed is being used to move through time. You are traveling through time at the maximum possible velocity. That's why you're aging. You are hurtling into the future at the speed of light. Now imagine you get in a rocket ship. You start to move through space. You are turning the wheel. You are diverting some of your velocity. You are taking it away from the time direction and putting it into the space direction. So, because you are moving through space, you must move slower through time. That is time dilation. That is why the astronaut ages slower. He isn't experiencing magic. He is just changing his direction in space-time. Now, what happens if you put all your speed into space? You turn the wheel all the way. You use 100% of your velocity for spatial travel. Well, if you use 100% for space, you have 0% left for time. Time stops. And that is what light is. Light is something that has rotated its velocity entirely into the spatial dimension. It has no speed left for time. So you can't go faster than light through space because you can't be more than 100% committed. You can't drive north faster than 60 mph if your car's top speed is 60 mph. You are already maxed out. We are all traveling at CG. Light just happened to do it horizontally while we do it vertically. Doesn't that make you feel a little better? You aren't slow. You are just moving in a different direction than the light beam. You are a time traveler. Now let's get back to the why. Why do we have mass? Why are we stuck in the slow lane? If everything is naturally moving at c, what slows us down? This brings us to the Higgs field. They are a very modern discovery. Peter Higgs and his friends predicted it in the 1960s, and we found it in 2012. Imagine the universe is filled with a thick syrup, or a room full of people at a cocktail party. This is the Higgs field. It's everywhere. Now, some particles, like the photon, they are like ghosts. They pass through the cocktail party and nobody notices them. They zip through the crowd at top speed. But other particles, like the electron or the quarks that make up your body, they are popular. As they try to move through the room, the people at the party cluster around them. Hey, look, it's an electron. They clump. They interact. They slow it down. This clumping, this resistance is what we call mass. Mass isn't a thing you have. Mass is a measure of how much you interact with the background field of the universe. You are heavy because you're swimming through molasses. If we could turn off the Higgs field, snap instantly, all your atoms would lose their mass. And what would happen? You would explode. Well, not explode like a bomb. You would cease to be solid. All your particles, the electrons, the quarks, they would suddenly accelerate to the speed of light. They would fly apart. You would dissolve into a spray of radiation moving at sea. Biology would be impossible. Chemistry would be impossible. Atoms wouldn't hold together. So the reason we are here, the reason we can sit and think and drink coffee, is because we are slow. We are the sluggish ones. We are the ones that got stuck in the syrup. And thank God for that, because complexity needs time. Structure needs stability. If everything was flying around at the speed of light, nothing could ever settle down to build a DNA molecule. Nothing could ever build a brain. The slow lane, the world of mass, is the only place where life can exist. So we shouldn't be jealous of the light. The light is fast, but it is dumb. It can't stop. It can't think. It can't feel. We pay a price for our existence. We are heavy. We are slow. We are trapped in time. But the reward is that we get to be real. We get to be solid. Now let's talk about what happens when light does interact with matter. Because I said light always travels at c. And that's true in a vacuum, in empty space. But you know that light slows down in glass or in water. That's how lenses work. That's how your eyeglasses work. The light hits the glass and slows down, bends and focuses. But wait a minute, didn't I just tell you that light can't slow down? That it must go at c? Am I lying to you? No. This is where the atomic picture is important. Imagine the photon entering the glass. The glass is full of atoms, electrons. When the photon comes in, it hits an electron. Look, the electron absorbs the photon. It swallows it. The electron gets excited. It jiggles. It holds on to that energy for a tiny, tiny fraction of a second, a delay, and then it spits it out. It creates a new photon identical to the first one and sends it on its way. That new photon travels at c until it hits the next atom. Oh, absorbed, pause, spat out. So the light between the atoms is traveling at the speed of light, fast, but the process of stopping and shaking hands with every atom along the way, that takes time. It's like a train that goes 200 miles an hour, but it stops at every station. The average speed is slow, even though the train is fast. In diamond, light slows down to less than half its normal speed. Because diamond is a very crowded dance floor, the photons spend a lot of time shaking hands. This is beautiful because it shows that the slowing of light is actually an illusion of the crowd. The individual photons never slow down. They just get distracted. Now, I wanted to talk about the cosmic implication of this speed. If we look at the universe, it is huge. The observable universe is about 93 billion light years across, but the age of the universe is only 13.8 billion years. Wait, how can it be 93 billion light years wide if light only had 13.8 billion years to travel? This is the expansion. Space itself can stretch, and here is the kicker. Space can stretch faster than light. The speed limit c applies to things moving through space. It does not apply to space itself. So right now, there are galaxies on the edge of our vision that are moving away from us faster than the speed of light. The space between us and them is growing so fast that their light can never reach us. It's like running on a treadmill that is going too fast. You run and run, but you move backward. Those galaxies are disappearing. They are falling off the edge of the world. Every day there are galaxies that cross at that horizon and are lost to us forever. We live in a universe that is slowly deleting its own history. If we lived billions of years in the future, the expansion would be so big that we wouldn't see any other galaxy.